So let's we continue from the previous topic is about the how to calculate the residual properties by using generalized correlations. This is uh, Lee Kessler and as well as real equations. Okay, so uh, for Lee Kessler you have to do the interpolations. Okay, from the appendix E. While for virials, you can calculate okay directly by using the equations, but it's only applicable for low to moderate pressure. Okay. Uh, I think I give you an assignments. Okay. Assignments. This one example 3 and also tutorial 6. So any of you can give me the answer for this example 3 first. How about a value of Z, HR and SR? I think anyone can write in the chat box. Anyone? Siapa? Tan Li Ting. Are you there? Tan Li Ting. Tan. Tan Li Ting. Can you give me uh, the answer? Tan Li Ting. Are you there? Nobody is there. Tan Li Ting is not there. Hmm? Let me check the attendance. Can you respond, Tan Li Ting? Tan Li Ting. Attendance. Can you give me the answer? Z, HR, SR. What is the answer? So maybe you can give me the value of uh, Z not first. Z prime. And then Z. You calculate, right? And then H naught. H prime. H. F. HR. This one. HR not. HR. Okay. Okay. And then what is the value for the SR not? SR. SR. Z. Z not 0.668. Okay. 0.668. Z prime. And Z. What's the value? Z. Okay. 0.669. Is that 0.669? HR negative 29. Okay. So is that give me the final answer, right? Yeah, then. Fine. 2, 4. Eh, this one is HR. Mana H? Oh, negatif 2, 9,9,4. Okay, do not forget this one. The unit. Okay, this one is joule per mole, right? Okay. As well as -7. Okay, -7.392 joule per mole per Kelvin. Yeah. Okay, that's the final answer. Okay, thank you, Izzat. So, yeah, for the answer, no need to privately send me the message. You can share with everyone. Okay, that's the answer. Okay. So how about S negative? Yeah, that's correct. Sunlighting. Okay. So how about 236? 236, I think you have to determine the delta H equal to delta H Ig minus A plus. Okay. So H2R minus H1R. Okay. So what is the value of delta Hij? What's the value? And this one, what is the value? And finally, delta H. Okay. Anyone can give me the answer? Anyone? Nur Umaira, are you there? Nur Umaira, can you give me the answer? This one already explain right how to determine. Okay, Nur Umaira. So you have to find at the steam table delta H equal to H2 minus H1. So H2 is this condition and H1 this condition. Okay, Nur Umaira, are you there? Nur Umaira. Nur Umaira? Tak ada. Saya check dekat attendance. Can you respond, Nur Umaira? Attendance. Are you there, Nur Umaira? Can you write in the chat box? Nur Umairah. Ada. Nur Umairah, are you there? John Ting. Okay, John Ting. I get Delta HIG 117. How you get this one, John Ting? Oh, per mall. Okay, okay. So steam is you find you get per mall, right? Why you convert to the mall? Okay. Steam table. What to? Okay. Is it you referring to a new book? Because my book is a joule per kilojoule per kilogram, meaning that joule per gram. So if 600.1 times with water, 18, one zero, jauh, H2O, 18 gram per mol. Hmm. So 600.1. So delta HIG 117. You have to check. If you convert to the joule per gram, how much? 620 joule. 620. Okay, 620 joule per gram. Okay, okay, okay. So almost lah. Because mine is 600.1 joule per gram. Ah, okay. So once you determine, you can get this one delta H. Delta H2. Okay. Can you determine delta HR2 and delta HR1 and give me the final answer delta H? I think it's okay. Maybe because of the interpolation, John Ting. Especially at the second condition, the final condition, right? So I don't think that's why our answer is a little bit difference, right? Okay. So, but you can confirm again. But this is my calculation. This is my answer. Maybe yeah, you're also is correct. Okay, how about delta H? Anyone? Nur Umairah, are you there? Umairah ada tak? Umairah tak ada. But awak scan attendance. So saya akan pangkah tau. Nama awak Nur Umairah. Umairah? Tak ada. So saya just I guess you will not attend lah this class. Nur Umairah binti Amran. Nur Umairah. Lama hang tak? Nampak tak screen? Komputer saya hang.
Tak nampak.
Sekejap eh.
Tak nampak.
Hah? Tak nampak? Tiba-tiba hilang.
Tak.
Okay, kejap eh. Sekejap. Saya punya hilang. Sekejap. Saya stop sharing. Okay, so for delta H, okay, my answer is negative 593.95 joule per gram. So please check. Okay, so please check. Okay, sekejap eh. Saya punya tiba-tiba hang pula laptop. Oh, Umairah, okay. Okay, okay. Nasib baik you respond. Okay. Eh? So for tutorial 6, the answer for delta H is equal negative 593.95, okay, joule per gram, while delta S is equal to negative 0.078 joule per gram dot Kelvin. That is the answer for delta S and delta H. Okay, so this for those who cannot get the answer, so that is the final answer. Delta H is equal to negative 593.95 joule per gram, while delta S is equal to 0.078 joule per gram Kelvin. Okay, so we continue. Okay. Okay. We continue on the next sections. Okay, which is a two-phase system. Okay, for pure substance. Okay, now we are deal already with the two-phase system. Okay, after this you're gonna deal with the two-phase system, chapter 11, chapter 12, and chapter 10. Okay, so what is the criteria for the two-phase system? Okay, generally if two-phase system, the fugacity, okay, liquid and vapor should be in equilibrium. It's similar. Similarly also for the Gibbs energy. If the vapor and liquid in equilibriums, okay, the Gibbs energy should be same. Okay, you have to remember that because it is in equilibriums. Okay, and later we're gonna deal about the fugacity as well and fugacity coefficients. Okay, in chapter 11 mostly on the theory how to determine the fugacity. So if your vapor phase is non-ideals, so you have to determine this fugacity coefficient. Okay, while in chapter 12, mostly we are focusing on the how to determine the activity coefficient. This is for the non-ideal solution. Okay, you have to remember because if in equilibriums, but your vapor phase and your liquid phase, solution phase is not ideals. Okay, you have to include this activity coefficient and also fugacity coefficient. Okay, but if your assumption is vapor is ideal, so the fugacity coefficient is equal to 1. Similarly also for activity coefficient, if your solution is ideal, so it's gonna be equal to 1. So if you still remember what you learned in mass energy balance, you use the Raoult's law. I'm not sure you still remember or not. Have you learned about that Raoult's law, modified Raoult's law? Okay, for the two-phase system, right? Maybe it's just Raoult's law, not modified Raoult's law. If modified Raoult's law is um, only the ideal part is on the vapor phase, while uh, the solution or the liquid one is non-ideals. Okay, so you have to determine the activity options. Okay, So this is important because once you use a modified Ross law, we have to determine the activity coefficient. Okay. Okay. Phase equilibrium for the system in pure substance. Okay. If you still remember that the PT diagram, right, when it's crossed from the liquid to gas to liquid, or solid to liquid, solid to vapor, right? There is a what we call it a boundary lah. Okay, if you still remember, if you when we cross, we call it as a phase transition. Okay, if PV, so you can see the clearly. Okay, but for the PT diagrams, okay, it's just a line, right? Okay, so generally it's for gas. Okay, this one is vapor. Just call it vapor. This one is liquid, and this one is solid. Liquid to vapor, vapor and liquid. This is a phase transition. This one. Okay, so whether it's melting, vaporization, or sublimation. Okay, so the molar or specific value of the extensive thermodynamic properties change abruptly. Of course, from the liquid to vapor. As we you calculate the what is it about the heat, latent heat, and also sensible heat, right? It's different, right? Okay, for the change in the phase, also change in the temperature, right? Okay, it's going to be different. The equation that you have to use. Okay, thus the molar specific volume of saturated liquid is different from the molar or specific volume at saturated vapor. This is also true for the other thermodynamic properties, such as the U, internal energy, okay, enthalpy, as well as entropy. Okay, so you have to remember that Gibbs energy for the pure substance is never change. Okay, they are coexisting in equilibrium, meaning that if you have a liquid and vapor, G liquid is going to be similar with the G vapor. It's already proved it when if you do calculation about the liquid for the water, right, and also vapor is a steam. If you calculate the Gibbs energy, it's going to be similar. Okay, because it's in equilibrium. Okay, so this is an example for the two-phase system, the derivations. Okay, if we consider the system which is a closed two-phase VLE, vapor liquid equilibrium, okay, with T, P, and L, and also NV, this is the number of mole. Okay, so we can see here that for the constant temperature and pressure, total G is equal to dGn, and this is what we call it the G liquid lah. Gives any partial Gibbs energy, and also partial vapor, because partial is some in vapor, some in liquid, right? Okay, so what we call this is what we call it. Okay, if we derive, and finally we can get the mole balance NV and also NL, right, for the closed system, and we can get GLGV. This is the criteria for the vapor liquid in equilibrium. Are you gonna learn more in chapter 11, okay, and as well as chapter 10. Okay, the fugacity, whether you have many phases until infinity, is going to be similar. For example, f alpha, f equal to f beta equal to f gamma, and so on. Okay, so once you check by using a steam table, okay, because we only have the data for the steam table, if you calculate, right, GH equal to minus TS, right? So the answer is negative 98.6. This is if you calculate at 100 degrees C, because at 100 degrees C is the boiling point for the water, right? So it's going to can exist vapor and liquid. Okay, so once you calculate the Gibbs energy for the liquid phase, okay, it's similar. Okay, so meaning that your Gibbs energy at vapor and liquid is similar. So this is true. Okay, must be in equilibrium. Okay, so that's why you can do the separations, okay, for distillation. Okay, so once we deal with the two-phase system, the equation that already explained previously is just like what is it, the Clapeyron, right? What is it, Watson, Riddle, right? Okay, so similarly also if you want to calculate the what is it, the enthalpy or the pressure, so you have to calculate by using Clapeyron equations, this one, or you can use Clausius-Clapeyron equations. Okay, so this is a delta H vapor. Okay, so you need this term lah. Okay, a differentiate of dP and also dt. Okay, similarly also you can express in this equation on the left side. Okay, so to solve this one, you need the P pressure vapor. Okay, P saturated lah. We call it P saturated. Generally, we call it P saturated because at the saturated vapor, right? Vapor pressure. So this is more related to the Einstein equations. Einstein equations, if you look at here, that give rough approximation of the vapor pressure relation to the entire range of triple point to the critical point. Okay, so you know, right? Triple point is this one. Here, this triple. This is critical point. Okay, valid for the specified T range and should not be used outside of this range. Okay, so if we deal with the wide range of the temperature, you have to use Wagner. This one. And this is more accurate if you want to use. Okay, so everything you have to see table B2 for determination of for the A, B, and also C lah, the constant. Okay, so and also D. Okay, so please remember that I think so for the new books they already stated the temperature range for each component. Okay, but outside of that temperature you have to use the weight. Okay. So for the non-polar liquids, okay, if you want to calculate the what is it? This one is pre-saturated. Okay, Lee-Kessler correlations. You can use this one also. Okay, so this is the equation. So it's almost similar like the Z equal to Z, not right, plus omega Z prime. So just use this equation and you substitute here. Okay, get the TR, 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 TR. Okay, so this is correlation was developed for the non-polar liquid for the saturated pressure. Okay, vapor pressure similar. Okay, this is a reduced vapor pressure. Okay. Okay, let's see the example. This one. This is a very long example. This is one of the good example, and you can read from the main textbook. Okay, if for the old versions, okay, please you can refer to the example 6.9. If new version, I think is B is 6.10 or 6.8. I think 6.10. Okay, for the 8th edition. Mine is 6th edition or 7th edition. Okay. Okay, so if you look at here, estimate VUH as for the 1 butane vapor at 200 degrees C and 70 bar if enthalpy and entropy are set equal to 0 for saturated liquid at 0 degrees C. Assume that only data available below TC, TN, PC, omega. TN is a normal boiling point and also CPIG. Okay. So if you look at there, okay, I just explain briefly. Okay, about the hypothetical part, right? Since you can read more detail from your main textbook. No need. So if you look at here, the first condition is saturated liquid, and then the final condition is the gas. Okay, so you have to remember, please understand the phase. Please determine the phase, initial and final, as well as you need to construct the hypothetical part. If enter is vapor and exit is vapor, so it's easy. Okay, or liquid and enter and then exit is liquid also is easy. There because there is a no change in the phase. There's a no, what is it? Cross the boundaries. Okay, if you see the PT diagram, right? But once it's a change in the phase for the system, you have to construct to see the clearly, you have to construct the hypothetical part. Okay. For examples, this one, right? Because the initial condition is saturated liquid. So you have to bring it to the saturated vapor. Okay. Please see the condition first. Right. Because the first condition is 273.15 Kelvin and 1.27 bar. Okay. So this is a saturated liquid, and then you have to bring it to the saturated vapor at the same temperature and pressure. Okay. And then you have to bring it to the reference state lah. Okay, the ideal gas. Okay, and then this one you know how to calculate, right? Because you already calculated, you can calculate at the ideal gas condition or reference state. Then you have to bring it to the final condition. Okay, so this is your hypothetical part. Okay. So if you look at here that this is a saturated liquid. Okay, this is saturated vapor. Similarly, also this is ideal gas lah, IG. Right? Okay, and then at different temperature, IG. And finally, the final state. Final state. So this one is 273.5 Kelvin, right? 1.2771 bar. This one delta H, delta S. Okay, and then saturated vapor with the same temperature and pressure. This one, same, also same here. Okay, because you just change in the phase, right? Okay, and then change in the this one lah. You have to bring it to the reference state lah. The same condition. Okay, but to here, okay, the condition is different for 73, but still under the ideal gas condition lah. Okay, 115 Kelvin, and then 70 bar. Okay, and from ideal gas to the final state. Okay, the same condition. Okay, okay, so meaning that you have how many part? 1, 2, 3, 4. A, B, C, and D lah. This one A, B, C, and D. Okay, for A, what equation that we have to use to calculate the enthalpy? What heat is this from liquid to vapor? Anyone? Azima? 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 Are you there?
Vaporization.
Huh?
It is vaporization.
Heat vaporization. Yes. What name of the heat? What is it? This one. Chapter 4. Is it sensible heat? Heat of reaction? What is it? Because liquid vapor.
Heat of reaction.
Heat of reaction. Why?
The temperature doesn't
No, this is just
change.
change in the phase. If change in the phase, what is it? Change in the phase. No change in the temperature. This one change in the temperature. Latent heat. Yes. Angjaying is a latent heat. So if you deal with latent heat, what equation you have to use? Okay. First equation is, what is it? What equation? Any candidate equation? Oh, apa? Zurhani, Fahzrin. What equation that you can use to calculate the heat? Here, example of the equation. Zuharni. Mana Zuharni ni? Are you there? Zulharni? Yeah, Azima, thank you. Latent hit. Ah, sorry. I just realized your message. Zulharni? What equation that you can use here for change in the phase? Hey, you gonna use this one, okay, until at the end of the chapter. Okay, this hypothetical part, the heat. If you can't understand the phase, the conditions, it's gonna be it's quite tough lah. Because this is only change in the phase. Later you're gonna include the reaction. Ah, Zurhani, Zurhani. What equation that you is possibly you can use now for two phase change in the phase now? Because Angjayi said this is a latent heat. Okay, so yeah, it's a latent heat this one because change in the phase. Any idea, Zurhani? Chapter 4, chapter 4. Just now also already mentioned. Anyone? Poyi? Poyi?
Yes, doctor.
What equation that we can use from chapter 4? Change in phase.
We can use the Clapeyron equation.
Clapeyron, yes. One is the Clapeyron. Okay, but we have no information here for the Clapeyron. So, what equation that we can use from the normal boiling point?
Troughton's rule.
Troughton's. Troughton is I don't think you can get the accurate answer. So we used to using a Riddle and as well as Watson. Yes, Riddle equation. ONG. Okay, because it's change. You have to remember. One is change in the phase. Use latent heat. If there is no change in the phase but change in the temperature, okay, sensible heat. Okay. Yeah.
Okay, thank you, doctor.
Okay. So this one is you will have to use the latent heat lah. Okay, and then you have to calculate the residue lah, HR negative HR1. Okay, so if you look at it there, okay, the pressure is very low for the residual. What equation that we can use for this one B? The pressure is only 1.2771. What equation that we can use? Anyone? Here, HR. You learn using a graph method, cubic equation of state, cubic equation of state, or you of course you gonna deal with the van der Waals, Reddick-Kwong, soft Reddick-Kwong, Penn-Robinson. And then the third one is Jonas correlation, Virial as well as Lee Kessler. Which one you suggest for this state, the residual? Anyone? Ikram? Which equation you can use for this area? And give me the justification. Justify your answer.
Use generalized and real
Virial. Okay, what is your justification?
was low pressure.
Okay, good. Okay, because it's low pressure. Okay, but if you deal with this one, because the pressure is 70 bar, so which equation for you, Ikram? You can use Okay.
Kessler correlation.
Kessler. Okay, you can use Lee Kessler or Penn Robinson. Okay. Okay. So I think you can understand. And then I think for ideal gas condition is easy, right? Okay, so the step C. So this one is what equation? I see pH. This one is for the enthalpy, okay, or ICPS or MCPH, MCPH. And this one, okay, chapter 4 also. You have to remember that. This is ideal. Okay, because it's just changed in the temperature from 273.15 Kelvin and 473.15 Kelvin. Okay, is it okay? Are you okay? Huh? Understand or not? Any question about this one? For details calculations, please refer to the example 6.8 or 6.9 from the main textbook. They already stated the step by step. Step A, how you, of course, you have to determine the saturated pressure, okay, pressure vapor, because you're going to deal with the Clapeyron equations, Riddle and also Watson. So you have to determine the saturated pressure. And then for the step B, right, this one, you have to determine the parameter for the virial generalized corrosion. And this one ICPH, of course, A, B, C, and D, right? Okay, A, B, C, and D, because it's just deal with the one component, only one component, meaning that the total A, total B, total C, and total D. Okay, ICPH, MCPS, MCPH, ICPS, MCPS lah. That one is for the entropy. Okay, and this one is Lee Kessler. Okay, because it's high pressure. Okay, any questions about this example? Is it clear, my explanations? If you don't understand, you can, yeah, can write in the chat box, or you can unmute your microphone. Any questions? Okay, so I guess no questions. Okay, you can understand. Faham eh? Nanti if you do the tutorial, I think you can understand. Zaki, what's it? Oh, Zaki is not here. Only Zaki. Okay, boleh? Okay. So let's we move to the two-phase liquid and vapor. Okay. So this is important to determine the fractions because you deal with the vapor and liquid, right? Okay. When the system consists of saturated liquid and saturated phase coexisting at equilibrium, the total value of the extensive property of two-phase system is the sum of total properties of the phase. So meaning that there's a fraction there. Okay, because yeah, maybe 0.5 in the vapor, 0.5 in liquid phase. Okay, so the total is going to be M is it applicable? Asal tak ada saya guna. Kerja. Okay. M is equal to this one is a fraction, right? If this one is 0.5, okay, so this one is 1 minus 0.5 lah. Okay, so maybe this one is a H, right? This one HL, this one HB lah. Okay, the sum of the for each phase lah. Okay, for the two phase system. Okay, total properties of the phase. Okay, if you want to find total M, right? Okay, so I think so all of you know, right? X L M L plus X V M V. Okay, that is important because composition. This is like a composition. In chapter 10, composition is the main parameter that you have to determine. Okay, so this is a mole fraction of the liquid and also vapor. We also know the quality, that is the mass fraction of the vapor in the system. Okay, things all of you know. Okay, so let's see example 5. What is it? Superheated steam at 500 Kelvin, right? What you have to do? And 300 degrees C expand isentropically to 50 kilopascal. What is the final enthalpy? What is the final enthalpy? Okay, because it's isentropically, what you have to do is first, please refer to the superheated steam table, right? Table F2. So if you look at there, P1 is given. P1 is equal to 500 kilopascal, right? And then T1 is equal to 300 degrees C. Okay, this one you have to convert to the Kelvin. Okay, isentropically. Okay, isentropically. P2 isentropic. Okay, and then P2 is equal to 50 kilopascal. Fifty kilopascal. Wait, maklum. Baik. Dan perkiraan 1/3 dan berikan. Okay, so you have to determine H2 lah. This one is enthalpy. Okay, so okay, from the table F2, okay, so at the first condition, this one, please determine S1, entropy at the first condition. Okay, joule per gram. The first condition. Okay, so once you determine, okay, the final state is at this entropy and the pressure of 50 kilopascal. So the final pressure is gonna be the state is wet steam. Okay, you have to see the condition. Okay, so table F2 you have to do interpolation. Yeah, so you have to do the interpolation. So you determine already S1. So what you have to do is interpolation. If you look at here that are you done this one? I just want to construct the table. Done, okay? Okay, so this is the pressure, kilopascal. Okay, 49.31. This one is 50, the final, and 51.33. Okay, and this is saturated liquid, saturated vapor. This one is for H, and also V. V, V pula. Allah, double click lah. So just like this, liquid, vapor, liquid, some vapor. Okay, so this one is a pressure lah, kilopascal. Okay, kilopascal just 49.31. This one is 50, and then 51.33. This one is enthalpy. This one is entropy. Okay, saturated liquid, saturated vapor. This saturated liquid. Saturated. This one saturated liquid, saturated vapor. Okay. So H liquid, H vapor, S liquid, S vapor. You have to determine. You have to do the interpolation. 339.1 into 6454 1.0871, and this one is 7.5995, and this one is 343.3, 26.47, 2647.1. Okay, SL is 1.0990, and this one is 7.5858. Okay, so please do interpolation to determine this one. Okay, so you have to determine HL, HV, SL, and SB. So you already determined the S1, okay, from the table F1. But the problem is we have to calculate the enthalpy lah, H2. Okay. So from the enthalpy equation, because this is asentropic, meaning that the entropy is the same at the first condition and second condition. Okay. Once you determine, okay, S2 equal to S1 equal to S liquid plus X, okay, S vapor liquid plus X S vapor minus S liquid. Okay, this is an equation just like a previous one. M equal to 1 minus X times with the ml plus xv times with mv. Okay, so rearrange this question, you can get X equal to S1 minus S liquid divided by S vapor minus S liquid. Okay, so you can get value of X. Okay, so once you determine X, okay, by the equation of H2 equal to H liquid, similarly, same expression, okay, plus X H vapor minus H liquid. Okay, so you can get value H lah, H2. Okay, HL and HB you can determine from this interpolation. SL, SV, once you determine, you substitute to this one. This one for blue. Please substitute to this one. Okay, and then you can get S is from table F1 once you determine. Okay, and this one also. Shell. Shell. Now this one is from here. So you can get H2. Can you calculate? What's the answer? S1. Okay, any questions about this one? Example 5. Okay, please do this one. And if you can answer, I will ask in the next class. Okay, before we start with the chapter 11. Okay, so please write down this one. Let's we continue. Okay. To determine informations, you can use the other method other than what we call it as a equation of state, cubic equation of state. What else? Generalized questions. You can determine also by using thermodynamic diagrams. Okay. So this is a relationship between the thermodynamic variables like temperature, pressure, enthalpy, right? Volume as well as entropy. So example, you have a TS diagram, PT diagram, especially PT diagram, PV diagram, pH diagram. PV, you can see the two-phase system more clearly compared with the PT diagram, right? So, but not all data is available. Okay, not all diagram is available. Okay, especially for the component is the new components, right? I'm not sure for the methane, but you have to determine from other engineering handbooks. Okay, so this is an example of the pH diagram. Once you know the pressure, non-pressure, so you can determine directly the hydrogens. This I think you can find for the CH4 and also tetra fluoroethanes. Okay, this is in appendix G. Okay, so from the appendix G, if you look at there, yeah, that is the pressure versus this is pressure, not ln P. From the you can determine the enthalpy directly from this diagram. Okay, so it's really this one is the pH diagram. So if you know the pressure, right, just make a horizontal and vertical line so you can get the enthalpy in kilojoule per kilogram. So this is, I think, is for new books. Mine is in the US unit BTU per pound mass. Okay, and the pressure is PSIA. Okay, so another pH diagram. This one is for the methane. Okay, if you deal with the methanes and you have to determine the enthalpy, just refer to this diagram. Okay, and this one is for methane SI unit. This one is a US unit. Yeah, SI unit. SI unit. This is a propane. Okay, if you do the project plan design, right, so you want to determine the enthalpy, so just refer to this diagram if for propane and methane. And another one is TS diagram. So if you know the temperature, so you will know the entropy. Just do the cross line, horizontal and vertical, so you can determine. And this is Mollier diagram. I think Mollier diagram is I'm not sure for the new book, but mine is old book. Okay, the old version. So I have this Mollier diagram actually. Okay, so you can determine directly, especially for the steam. We have many data about for the steam, whether in table and also diagram, but some other components is we cannot find the diagram and also the tables. Okay. Okay, and another method is, of course lah, you use a thermodynamic table such as a steam table, right? Okay, so you can read value thermodynamic properties. Is more accurate lah because it's from the experimental. Okay, so you just do the interpolation or extrapolation. For example, ammonia table, saturated table, compressed liquid tables. Okay, so you can. So after you complete this chapter 3 and also 4, so you have the fundamental for the pure substance actually. Okay, whether it's in liquid or vapor or in the two-phase system, vapor and liquid. Okay, so for the next actually we will deal with the maybe two component. Okay, binary, and it will be in the vapor and also in liquid or two-phase. This is going to be more uh, complicated lah kita panggil. So let's before we stop, what is it? Let's see which example is good. Okay, this one. Propane gas. Okay, let's do this one. Okay, propane gas at 1 bar and 35 degrees C. So you have to convert to the Kelvin, right? Compressed to the final state 135 bar 195 degrees C. Okay, estimate the molar volume of the propane in the final state and the enthalpy entropy change of the process. Okay, in the initial state propane may be assumed as an ideal gas. Okay, so you have to determine the final. So first condition, okay, P1, what else? T1, P2, T2. This one is given. Okay, this is ideal gas lah. For the initial, this is ideal, this is ideal. This condition. Okay, you have to determine V, delta H, delta S. Okay. So meaning that your hypothetical part is like this. Because it's starting from the ideal. Yeah. And this is your final. Right. Now your hypothetical part. Delta H, delta S. Okay. So you have HR here. HIG. You have to remember this one. Okay. Since you have to determine the volume, of course you will have to determine the what is it? TC, okay, omega, okay. And then you have to determine once you TC, you have to determine TR2 lah, TR2. Just calculate volume at the final pressure, right? Final condition. Okay. So since if you look at here that 135 bar, the equation that you have to use is Lee Kessler. Okay. V equal to Z RT divided by P. Okay, Z equal to Z naught plus omega Z prime. Okay. So to determine this one, interpolation. Okay. So determine Z and then phase find V. Okay. So that is the first step. Correlation by interpolation. Okay. Okay. So and then we have to determine the HR. This one is, I think, is easy by using the ICPH and also ICPS, chapter 4, right? Okay. Okay. And then next, you have to determine because 135 bar. Oh my. I think this one you have to use the Lee Kessler HR. HR prime HRM. So meaning that you have to do the interpolation. If you remember that, which one? HR equal to HR plus omega H R prime Allah. So this one you can eliminate. So you can get HR. Similarly, also for the SR equal to SR plus omega SR. Okay, you can get SR. Okay, so once you determine what you have to do is delta H equal to R I CPH. Okay, T1 T1 T0 yes, T1 and then T A B C D plus HR. Okay, okay, so you can get delta H lah. Okay, so for delta S similar also this one R and with the ICPS. Okay, minus ln P divided by P naught. Allah. Delta S equal to R dot ICPS. Okay. PS T1, T2, A, B, C, D. Okay. Minus ln P divided by P naught. Okay. So this one is plus SR. Okay, so you can get SR. Okay. So since the finals, if you look at here that the finals is high pressure, right? 135 bar. So you have to use the Lee Kessler. Okay, Lee Kessler correlation. Okay, any questions about this example, how to solve? Understand or not? Boleh faham tak? Ada soalan tak? Is it clear? Any questions? I think we covered already chapter 6, this topic. Before we stop. Any more questions? Any questions? Okay. So if you have no questions, next week, next week cuti Lupa pula. Okay. For the next class, cuti lah kan? Ke tak cuti? Raya kan? Oh iyalah, raya. Okay. So we finish our topic. Okay, and I will post the assignment. You have to submit after Hari Raya. Okay. And then we will have a test one. Okay. Any more questions? Okay. So that's all for today. Thank you very much. And for those who still not scan the QR code, please scan, okay? Mana mak tak keluar pula. That's all. Thank you very much.